We're going to be switching gears a little bit. The previous module we talked about thunderstorms, severe thunderstorms, and tornadoes. And for this module, we're going to be talking about hurricanes, and then I'm going to talk a little bit about superstorms and other types of extreme weather. So, obviously, in the last few years, we've had a lot of major weather events, storms like Superstorm Sandy, and then in 2017, we had a major outbreak of hurricanes with storms like Irma, Harvey, Maria. And so we're going to talk a little bit about that in this particular module. So without further ado, the first thing we need to talk about is tropical weather. So much of what we've talked about up to this point in the course is primarily for the mid-latitudes. That's the region that primarily represents in between the Tropic of Cancer and the Arctic Circle here in the Northern Hemisphere, and then the Tropic of Capricorn and the Antarctic Circle in the Southern Hemisphere. However, for the purpose of this class, we live in the mid-latitudes. But today we're going to be looking more near the equator and talking about tropical weather. Some of the goals for this first lecture video are to first understand how weather behaves in the tropics. Then we're going to talk a little bit about what are called streamlines and how you can detect tropical waves from them. And then we're going to talk a little bit about how tropical cyclones begin to form. And then in the next lecture, we'll specifically talk about hurricanes, how they get their names, the hazards posed by them, how we categorize them, the difference between a hurricane and a typhoon, and so on. So first we're going to talk about the tropics. And the reason why we need to talk about the tropics, other than the fact that we've already talked about the mid-latitudes ad nauseum, is the fact that hurricanes typically form in the tropics. And as I mentioned a few moments ago, we define the tropics as this area near the equator. And it's actually a belt between the Tropic of Cancer, which is latitude 23.5 north, to latitude 23.5 south. That's the Tropic of Capricorn. And that belt also covers the equator. In this region of the world, weather is a lot more defined by, seasons are a lot more defined by not so much what time of the year, but what time you are getting rainfall. And the reason why is because in these regions, in the tropical regions, the sun is always high in the sky. So you always have intense amounts of solar radiation coming in, regardless of the time of year. So there's lots of moisture and heat. And as a result, there are lots of thunderstorms. One other key ingredient, though, in the tropics is this band of low pressures called the Intertropical Convergence Zone. So if you remember from a few modules back, we talked about what was called the three-celled model of atmospheric circulation. And I mentioned that there was a belt of low-pressure systems that form over the equator because that's where the most sunlight is, that's where the most warm rising air is, and hence this band of low pressures develops there. Well, we actually call this band of low pressures the Intertropical Convergence Zone. Now, one of the things that I didn't mention so much when talking about the three-celled model is that in real life, the sun travels north in the summer, south in our winter months. So north in our summer months, south in our winter months. And as a result, this Intertropical Convergence Zone travels to the north in our spring and summer months and travels to the south in our fall and winter months. This is important because it's this Intertropical Convergence Zone that allows tropical systems, tropical cyclones to develop. And during the spring and summer months, it's in the northern hemisphere. So that's why we actually get a lot of our tropical cyclone activity during the summer months. And this image actually shows that concept. So if you take a look during our winter months, so January, February, December. The intertropical convergence zone is usually south of the equator. One thing I'll mention about the intertropical convergence zone is if you notice wherever it's over land, it makes a slight poleward kink, meaning that there's an area that points a little bit closer to the poles. This simply happens because land ends up getting a little bit warmer. Because it's a little bit warmer, there's more rising air. That causes the intertropical convergence zone to bend a little bit. For the most part, that's beyond the scope of what we need to know. All I want you to know is that this band of low pressures, this ITCZ, is in the southern hemisphere during January, again, December, February, our winter months. Up here in the northern hemisphere, when it's winter for us, the ITCZ is in the southern hemisphere. On the other hand, when you get into our summer months, so now we're talking July, August, June, September, the months where the sun is over the northern hemisphere, the ITCZ travels north too, and it ends up in the northern hemisphere during those months. And so this shows us the average position of the intertropical convergence zone during the summer months. So this happens during the summer months, during our summer months. Now, the intertropical convergence zone is a band of low pressures, and therefore a lot of stormy weather develops on the intertropical convergence zone. And if you remember from the Walker circulation, where you have warm air, you have rising air, there's lots of moisture in that rising air, so there's a lot of thunderstorms that develop along the intertropical convergence zone. And you can see this from any satellite image where you see a band of clouds and stormy weather near the equator. That's the intertropical convergence zone. Down near the equator, winds are typically blowing from east to west. If you remember from our discussion on global circulation, on ocean currents, a few modules back, we actually talked about this idea that winds typically blow from east to west, and we call these winds the trade winds. And they're called the trade winds because major trade routes use them to travel from east to west. And these are pretty reliable winds. These are actually pretty constant. They vary, but they're very reliable, meaning that they're almost always there. With that said, these winds actually end up acting as a way, a method that we can detect the formation of tropical cyclones. And the reason why is because near the equator, temperature differences aren't very great. And as a result, pressure differences aren't very great. We call that a barotropic atmosphere. You don't need to worry too much about that term. Just know that down near the equator, pressure differences aren't very great, temperature differences aren't very great. So we can't look at temperature and pressure the same way we would in the mid-latitudes. Instead, we have to use something called streamlines. And these streamlines are basically just lines that diagram how the wind is blowing down there, down near the equator. And these streamlines help us identify wind flow patterns. Well, what happens is, in the event that a tropical wave develops, and a tropical wave is basically like the predecessor to a hurricane. I always like to call it a wannabe hurricane. Basically what happens is a very weak, low pressure area called a tropical wave develops. Now, if we remember, here in the northern hemisphere, low pressures rotate counterclockwise. And as a result, you notice a little bit of an up and down kink in a streamline. And I'll actually show an image of this in a moment. And it looks like a little wave, hence the term tropical wave. And these waves actually form on the intertropical convergence zone. So first, let's talk about the trade winds again. So again, just a review from several modules back. Near the equator, winds blow from east to west. If we take a look at the streamlines, which again just diagram how winds are flowing along the equator and along the intertropical convergence zone, what we look for is a place where the winds suddenly take an upward kink, so up towards the north, and then turn back down towards the south. And this is indicative of a low pressure system. This is actually indicating some kind of circular motion. And in this case, counterclockwise motion, which is what we expect when we see cyclonic motion. So we see that here. In front of this tropical wave, these streamlines are moving away from each other. That's called divergence. Divergence promotes sinking air, and so you don't get any real stormy weather here. On the other hand, here on the eastern end, the right end of this what we call a trough or a tropical wave, on the eastern end of this tropical wave, streamlines are converging. Convergence promotes uplift. Uplift promotes thunderstorm activity. And so thunderstorms begin to develop here. And these thunderstorms are sitting over a region with lots of heat and lots of moisture, because now we're in the tropics. So there's lots of heat, lots of moisture. That allows these thunderstorms to continue to grow and continue to develop. Well, if the conditions are right, what'll actually happen is this wave that has developed will begin to become more pronounced. And it will transition from just a kink in the streamlines to a full-blown cyclonic motion. And when that happens, the tropical wave then develops into what we call a tropical cyclone. And when the conditions are favorable, we see this happen. Now, these tropical cyclones exist in different stages of development. Here in the Western Hemisphere, so in the United States, we refer to these cyclones in 3 different stages. The 3 different stages are tropical depression, tropical storm, and hurricane. Now, if you've ever lived in East Asia or in the Southern Hemisphere near Australia, you've probably heard different terms used for tropical cyclones. In the next lecture, I'm going to talk a little bit more about those terms, and we're going to really delve deeper into the concept of a hurricane. So make sure you join me for that.